Hello and welcome to another one of these ADD videos. Today we're going to be looking at LeChatliers Principle. LeChatlier came up with a way to deal with how the equilibrium of a reaction will be affected whenever it gets upset by an outside influence. What change does it undergo to try to restore this equilibrium, if at all possible? Okay, so what are some of the changes that can occur? Well, we could add some products or reactants, and if we do add some products or reactants, the equilibrium shifts to remove it. What does that mean? Well, let's see, if I have reactant product, if I add reactant, for instance, let me do that in a different color. If I add reactant, for instance, what's going to happen is the reaction is going to shift to the right to compensate for this extra reactant that you've put into the scale. So if you want to think about it as a seesaw, it was balanced, okay, and then you put a little extra on that side. Right, we had the R and the P, they were nice and happy, and when you put that little extra on that side, what happened? The scale tends to tip down a little bit. Okay, so what must happen is some of these reactants must now get converted over to products so that the scale can then rebalance itself. So the equilibrium would shift to the right if we added reactants. Sorry, if we added products by the same concept, we would shift the equilibrium to the left. Okay, hopefully that makes sense. If we remove reactants and products, so again we got the same scenario going on here, and we subtract, let's say, a reactant, well, I have to now compensate for that reactant that I took place by giving some of the products back over that way to compensate. So let's see if we can try to get that seesaw analogy again going. Balanced at the beginning, and what happens? We take away some of the R. Let's make it a lowercase r to signify we've lost some of the R. And that line, that scale, tends to lean to the side of the reactants. So to shift the equilibrium, some of this product now has to go to the reactant to restore the balance. So it does that and restores the balance by giving it some of it that way. So if we subtract reactant, the equilibrium shifts to the left. If we subtract product, the equilibrium shifts to the right to replenish both of those that have been taken away. Now for volume change, especially decrease, it's a little tricky. It all depends on the volumes of or the moles of gases. So if we look back to that example we had earlier, when we were looking at the formation of ammonia. Oops, sorry. In this case, let me balance it. The left side had 4 moles and the right side has 2 moles. So if we were to decrease the volume, the reaction equilibrium would favor the side that had less moles. So in this case, the equilibrium would get shifted to the right. Alright? So it's all about lowest side. Now if they had both 2 on each side or both 4, then there would be no change in equilibrium no matter how much we compressed it. Alright? Now the heat depends on whether we're exothermic or endothermic. Endothermic has heat put into the system. If you remember the potential energy diagram for an endothermic graph, potential energy being the y-axis, we have something that looks like this, in which the products have more energy than the reactants because of the heat being put into the system, or the energy. And then exothermic is something like that. Alright, so if I add heat, for instance, to an endothermic reaction, that would be like adding a reactant, and the shift would go to the right. And if you remove heat, it would go to the left. And that would be just applying the 2 top rules up here of adding and removing. It's just now a reactant because it's endothermic. And then exothermic, if I add heat, it would push it to the left, opposite endothermic. And remove heat, push it to the right. And this is only for exothermic. Okay? So you can see there's some specific principles that dictate which way the equation will shift its equilibrium due to an outside change or influence or disturbance. How will it restore that equilibrium, if it can at all? Alright? So make sure you check out the example videos for LeChatliers Principle, and practice, practice, practice. Thank you and have a nice day.